bases are proton acceptor. Right? These tend to be all metal oxides, right? Oxides and hydroxide, right? Calcium oxide, magnesium oxide, sodium oxide, right? You could also have calcium hydroxide, right? Sodium hydroxide, right? So they are basically opposite to the acid, alright? And they further define a base as in an alkaline is a base which dissolves with water to form a solution that contains OH minus ions, right? So you also need to know about alkaline, right?
Luminary will after this.
To form solution that contains OH minus ions, right? So these would be all soluble oxides, right? So sodium hydroxide, potassium hydroxide, ammonium hydroxide. Remember that all sodium, potassium, and ammonium salts are soluble, or the hydroxides are soluble, like, right? All sodium, potassium, and ammonium compounds are soluble. So even when oxides and hydroxides tend to be insoluble, the sodium, potassium, and ammonium hydroxides are all soluble. They are exceptions. Alright, so I'm just going to read this. So, general properties of aqueous alkalines. So, they are bitter in taste, they are corrosive, they are soapy, they change red litmus paper to blue, the pH is greater than 7, and they also conduct electricity like the acids. Alright, so remember that in terms of pH, you're above 7.
The bases are bases.
Alkaline, yes. But they are the bases that dissolve in water, form hydroxide ions. Alright, or alkalines. Alright?
Corrosive, red.
Soapy, red litmus to blue, pH greater than 7, and they are electrolytes. Those you can just write them down. Alright? So chemical reactions of bases now. Alright? So we would know one already that acid react with base, so base react with acid. That would be one of the reactions of base, reacting with the acid, right? Next one is that base react with ammonium salt, right? Water again, so we use calcium. Alright, and 2 we have a base plus ammonia, right? Solid ammonia plus water. Right? Example, sodium hydroxide plus ammonium chloride ammonia is a gas plus H2O liquid. I think that's balanced. Okay. That is 4, 5 hydrogen, 3, 4, 5, 1 H. It's balanced. Okay. Any question? Going once, going twice? Straightforward. So we have seen 3 reactions of acid and 2 reactions of bases. Alright? Well, basically 4 for the acid, because since the split carbonate and hydrogen carbonate reactions is different. Alright? Remember that, please ensure that you write the correct formula, right? So this is Na plus OH minus 1 minus. So that is why the compound for the formula for the compound is just NaOH minus. This is ammonium plus, so this is NH4 plus as the cation, right? This is ammonia gas, so this is a molecule, NH3, right? Alright? So we have to know the indicator. Most likely we use phenolphthalein or methyl orange, right? So indicator, coloring acid, coloring alkali, right? So in can't spell this right. PH. Naphthalene, right? PHA. Alright, so we are familiar with litmus because we talk about it every day. Alright, so in acid it's red, base is blue. Right, but you have to be familiar with methyl orange and naphthalene for that practical exam. They will use these as the indicator when they do the titration. Alright? So red, yellow. Red, green. So if you want to just start sweating now, you can see that acid is red for most of the stuff, alright? Colorless. Alright, so it's important that you know about this methyl orange and the phenolphthalein, definitely for the exam. Those are two popular indicators that they use, especially the phenolphthalein. Colorless to pink. They love this one because whenever you see the end point, the solution is going to change from colorless to pink sharply. Alright? So especially the phenolphthalein, you should remember this one. Alright? It's very common for the practical paper that they use phenolphthalein. Alright? So definitely they're going to have the acid in the burette. They're going to have the base in the burette and the acid in the round bottom or the conical flask, alright? Because they're going to put the indicator in the solution in the conical flask, which is going to be the acid, and they want it to be colorless. And you continue to add the base until you just see change to pink, and we know that's the end point. They can use the indicator, but sometimes they also use the temperature rise and fall to determine the end point for the reaction, alright? Alright. Next we're going to look at the strength of acids and alkalis. Alright? You have this? Right? You have strong acid and you have weak acid. And you have strong alkali and weak alkali. Right? So we have STRON, strong acid. And you have weak acid. Right? Strong acid, an acid that dissociate fully or ionize fully in water. Alright? Well, a weak acid partially ionized. Alright? So that's the important thing, fully ionized, partially ionized. Alright? In both cases. Alright? So a strong acid.
Hydrochloride.
Example of it? The hydrochloric acid. So all the acids that I wrote on the board earlier, they are strong acids. Alright? The weak acids are organic acids, such as ethylenic acid and those acids. Alright? Strong acid, see that this ethyl H2SO4. Right? Weak acid partially example of this is all organic acid. All organic acid. So ethanoic acid, methanoic acid, CH alright. This is ethanoic acid, methanoic acid, right? Strong alkaline that fully ionized in water. Example, all the alkaline that we use so far: sodium hydroxide, potassium hydroxide. Alright? We alkaline partially. Right, and the example of this is ammonia, right? So NH3 alright, we go to, you can still use the equilibrium sign, alright? Show that it's partially ionized, right? And the same thing we would use if we have a carbon, ethanoic acid is the equilibrium arrow we would use when it's a weak acid or a weak base. Okay? And look at unbuttered. Right? So they react with both acid and strong alkaline to form salt and water, right? So if we went back to qualitative analysis, it's because of some amphoteric oxide where we have those reactions that we're talking about, right? So, example, aluminum, zinc, and lead oxide, right? Aluminum, zinc, and lead oxide are amphoteric oxide. And the example that I'm going to use is to show the reactions. the acid, and this is with strong base, right? Same zinc OH2. So here. So there's a sodium zincate, is this? CAT. Alright, so as you can see, ZnO, this is like zinc oxide. So ZnO2, 2 minus, and then you have 2 sodium. So that's what will react when we react the zinc hydroxide with a strong alkaline such as sodium hydroxide. Alright, so it's an example. So this is why it's an amphoteric oxide. It reacts with both acid and strong alkaline. Good? So that is why in qualitative analysis, when you have a zinc, aluminum or lead cation, and we add the sodium hydroxide to form the white precipitate, if we should add excess sodium hydroxide, the precipitate dissolve. That's because the zinc, aluminum or lead hydroxide that is formed initially will react with the excess sodium hydroxide to form like the zincate or the aluminicate or whatever which is soluble. So that is why the precipitate will dissolve in those cases. Right? Giovanni? You're not following, or you didn't come to that class?
Oh, so you said.
He didn't come to the qualitative class.
I think I don't know sure. So when alcohol, when you put alkaline, and you put enough
If you add the excess strong alkaline to the amphoteric hydroxide, it will form a salt as well, a different salt. Good, like this.